You have been hired to paint 3 large non-overlapping circles, red, blue, and green, on the side of a building. The individual sizes of these circles was left to you. However, the total area must be 200 pi square meters. The contract gives you 3x gold bars for painting the red circle of radius x, and of course, you know, gold bars is a very standard way to pay people for painting. 4y gold bars for the blue circle with radius y, and 5z gold bars for the green circle with radius z. What is the greatest number of gold bars you can get from this project? So there's some options here: 80, 100, 125, 150, or 200. Do we have an answer? Do we have a guess? C. That's a lot of gold. We can't make that much. B. Only can make 100 gold bars. Now, this one might feel a little bit different from the previous ones we did, because there's actually 3 variables involved, but the same philosophy holds. We have a constraint, namely that the total area is 200 pi. So you get the pi x squared plus pi y squared plus pi z squared equals 200 pi, because we know how to find areas of circles. So that's our constraint: x squared plus y squared plus z squared equals 200. We're also trying to maximize our gold bars. So that's 3x plus 4y plus 5z. So it's an optimization with constraint. Set up, gradient of f equals lambda gradient of g. And the goal for gradient of f equals lambda gradient of g is to say, I want more relationships between x and y. The constraint gives me one. I want more. And so we set up the system of equations. Namely, we have that 3 equals lambda 2x, 4 equals lambda 2y, 5 equals lambda 2z. So here I can solve for 2 lambda, just as well as I can solve for lambda, but everything has a 2 lambda, why not? And I see that 3 over x has to be 4 over y, has to be 5 over z. So if I pair them up, so for example, the first 2 and the last 2, I can figure out relationships to say, oh, I can replace y in terms of x, I can replace z in terms of x, and now instead of saying x, y, z, I have x, x, x. One variable. Ah, I like one variable. That gives me hope. So we go to the constraint, plug in our relationships that came from gradient of f equals lambda gradient of g, and we can solve for x. So in particular, we get down to x squared equals 36, which means x equals 6. Now you might say, whoa, what about negative 6? You can't paint a circle with negative radius. It's not, doesn't work. I mean, you could say like it's a black hole, but no, that's not true. It's ridiculous. So you can throw that out as an option. So we only get one choice. So you get x equals 6, y equals 8, and z equals 10. Plug that in, and you get 100 gold bars. And there you go. Now, one of the things this shows you is you might say, if you were being very naive about this, you said, okay, what should I do? Well, I get the most gold bars for the green circle, so I should make the largest green circle and just not even paint the other 2. That might be your first intuition. It turns out that doesn't get you the greatest number of gold bars. So optimization is about trade-offs. The problem is, if you paint a big circle, as your radius gets bigger, your area increases rapidly. And so in some sense, small circles, you can get a lot of radius without a lot of area, but the bigger your circle gets, that's not true. And so there's these trade-offs. And at the end of the day, optimization is about trade-offs. You say, look, I have these various things, and I'm trying to figure out what's the right trade-off that gives me the most bang for my gold bar. All right. So there we go. All right. Thought for today. Now, this quote there are 24 hours in a day, and if that's not enough, then there are also the nights. So if you try to search for this quote and you go online and you dig around, you'll probably find out it comes indirectly from me. Not that I said it, but I'm quoting a friend who would say this. So I knew somebody who was one of those ridiculously high achievers in life. You know, member of the National Academy of Sciences, Hungarian Academy of Sciences, president of the mathematical societies, multiple mathematical societies, just did everything. And in addition to that, you know, he, in his early life, was a world-class trampoliner, all sorts, president of the International Jugglers Association. And it's just like, how? How did you do all of this? There's just not enough time. And so this was one of the things that he would say. And so I brought it up to him a few years ago. And he said, well, yeah, that one's okay. But the one I like to use now is that there are 24 hours in the day, and that's true every day. And I think that sort of captures how do you become effective. And you know, you might try to say, let me just overload myself. And I don't think that's good. You may have heard of this sort of notion of burnout. That's a real thing. And you can try to do too much. You can try to go too fast and try to do everything at once. What you need to do is just to make the best use of the time that you have. Every day you have 24 hours. Just make the best use of that. And you know, sometimes that might be going to jump on a trampoline. That might be your best use of that time. And so that's the thought for the day. All right. Now, on to the theory. Okay. Well, today we're starting in the third topic of the course. So you could say that multivariable calculus has three phases. In phase one, we talk about geometry. And we're trying to understand how do we describe things. And in particular, we spend some time understanding vectors and how to sort of use vectors in interesting ways. Then we go into phase two, which is to say, how do we describe how things are changing? In other words, the derivative part of calculus. How do things change? And so we figure out, what we can do is we can use the tools from single variable calculus and sort of take derivatives in each direction, combine all that together in the gradient, and get all sorts of wonderful information about how things change. Now we're in the third part, which is integration. Integration is saying, what's the total? How much is there? And so that's going to be for basically the remainder of the course. And we're going to go through some interesting directions. And so we're starting out with some basic ideas. So, okay, let's think about what we did before and what we should be doing now. So our generic plan says if I want to find the totals, I break things into small parts, I add up those pieces, and I get a total. That's still the plan. Now, when we have a function of a single variable, we would talk about, well, there's this function f of x, it's on this interval from a to b, and we say, okay, what do you do? Well, you chop up this interval into small pieces, and then for each part, you're trying to think of it as this small little strip here. You say, well, this is about a rectangle. It's not exactly a rectangle because the flat's not exactly top. The top is not exactly flat. I got the right word, it's just the wrong order. But it's rectangle-ish. And so we can say, well, we have the height of the rectangle. That's our f of xi, our height. The delta xi, that's capturing the small change in x. That's our width. Height, width, that's our area. And we're adding them up. And if we have a nice function, then this goes to a number, and we represent that number using this notation. And we'll talk about the phrase integrable. And generally speaking, what kind of functions are nice? And the punchline is that for us, nice equals continuous. Now, you can be slightly discontinuous, but more or less, if you're continuous, you're nice. That's how you should think of it. Okay, so that was the old us. What about the new us? Well, we'll start with a very simple case. So now we have not one input, but two. Okay. So what should we do? Well, now instead of going from A to B, we might be going over some region. So this might be A to B in the X direction, and it might be going from C to D in the Y direction, for example, for a rectangle. But we'll do the same philosophically. We'll say, okay, well, we'll think about breaking it up into little pieces. So I take a little tiny piece of my domain, just like we took a little piece here, and then we go up to our function, and there's a piece upstairs. And we say, well, hey, you know what? This looks like a very tall, thin box. And so I can think of it as, what if I want to find volume? You know, just like we talked over here, we have quote-unquote area. We can have volume, again, quote-unquote volume. Well, okay, great. What I can do is I can say, what's the contribution from this little piece? Well, I need a height, and I get that from using the function at a point. So that's this part, the f of xi, yi. Then I need a little bit of area. So usually at the beginning, we'll think of it as there's a little bit of change in the x direction and a little bit of change in the y direction, but it's a small rectangle, so it's a little piece of x times a little piece in y gives a little bit of area. And when this becomes a number, we say it's integrable, and we represent it as the integral over the region R, f of xy dA. Okay, so same words are being used, same ideas are true. If it's continuous, it's nice, it's integrable. Let's just make a comment here. What do you notice going on? Double integrals. What do you think that's telling us? Yeah, so it's telling us something about how the inputs of our integration are sort of like what we're integrating over. So this says we're integrating a two-dimensional type object. Here we're integrating over a one-dimensional type object. So we only have one input. Here, two-dimensional. Now you might say, could we have three integral signs? Yes, it's coming. But not till after the next exam. We've got to wait a little bit, but it's coming. Could we have four? Well, not in our class, but you theoretically can, right? You can always add more and more layers. All right, so that's the idea. Let's talk about some basic concepts. Any questions about the basic idea or underlying principle? Okay. Some simple properties. None of these will be very surprising. If you integrate 1 over your region, the result is area. And you might say, well, why would that be true? Well, what happens if you think about what the integral says is you say, break up your region into little pieces. And you say, okay, what's the contribution of every little piece? It's 1 times the area of that piece. So if you add up the little pieces of area, the result is the total area. Okay, so that's not too surprising. The other thing which is not going to be surprising to us is that we have that integration is linear. So whenever you hear the word linear, it just says it gets along well with addition and scalar multiplication. So if I have a constant, I can pull it out of the integral. If I see a plus sign, I can break it into two parts. So that's what linear means. I get along well with addition. I get along well with multiplying by constants. If I have one function that's below another function on my region, then the integral of one function is below the integral of the other function. And that makes sense because if you think about breaking things up into pieces, you say, well, the contribution from the piece for f is going to be less or equal to the contribution of the piece from g. So if you add up a lot of things which have the inequality, you still preserve the inequality. So that's not a surprise. And the last thing says you can break up your region. So suppose you have R is two regions. So you can split your region, big region, up into two smaller regions. Then the integral over the whole region can be thought of as the integral over the first region plus the integral over the second region. Now this can be useful in some cases. For instance, suppose your function f has different behavior over the two different regions, and you say, well, break it up into the two regions, and life is good. There are cases where, well, I don't want to get too far ahead and spoil the surprise. There are cases where initially it looks like two integrals, but by a very well-chosen way to re-represent the integral, you can merge it into one. Okay, but that's more of a next time type discussion. Okay, so those are some basic ideas. No big surprises. So let's try this out. We have R is a region where it says x goes from 0 to 2 and y goes from 1 to 4. So let's sketch our region R. So I'm going to think of it as a region in the xy plane. So we have x and y. X is going from 0 to 2. So 0 up to 2. Y goes from 1 up to 4. 1 up to 4. So we are a rectangle. There's our region R. And we're told that if we integrate over this region R, the function f of xy, we get 7. Now we don't know what the function is, we just know what the integral is. And we're asked to say, what's this integral? 3 times f of xy minus 5. What can we do? There was a great word over here. Somewhere? Separate. Which tool is the separating tool? Because there's kind of like two things that have this sort of notion of separation. So it's this kind of separation we want to use here. It's linear. This one is if we're splitting up our region. We're not splitting up our region. We're taking advantage of the fact that we have a plus or a minus. And by the way, a minus is really the same thing as a plus. It's just you're adding the negative of that. So we can, using linear, say, okay, well, if this is our integral, what can we do with the 3? Yeah, we can move it out front. 3, f of xy dA. And then minus, the 5 is also a constant. We can pull that out, integral. But if I pull it out, what am I integrating? Yeah, I'm integrating dA. Sometimes we could say 1 dA or just dA. All right, so using linear, then what? Well, do we know this first one? Okay, yeah, they told us. So it's 3 times 7 minus 5. Do we know this one? What is it? It's the area. So how much area is there here? Right? It's a 2 by 3 rectangle, so the area is 6. So we get 21 minus 30, which is negative 9. Are we okay with the negative answer?
Yeah.
Yes. Now, you might say, I'm not comfortable with it yet, but you have to remember, integrals are not just areas, integrals are not just volumes, they're totals. And you can have negative totals. You can go negative. It's okay. Now, there are certain settings where you say, oh, this integral is supposed to represent something. And in that case, you might say, oh, a negative is not what it's supposed to be. And then you should be worried. But in general, there's no reason to say an integral that you meet as you walk down the street, there's no reason it can't be negative. That's perfectly fine. Okay. Well, this seems fine, but how do you actually do it? Okay. So that's what we want to talk about. Let me just get my notes here. So we're going to do integration using an idea called iterated integration. So iterated integrals. So let's start with a very simple case. We're going to have a rectangle downstairs. So right now, our region R, so here's our region R. R is A less than or equal to X, less than or equal to B, C less than or equal to Y, less than or equal to D. So I have this rectangular region. Now, the way we presented it just a few minutes ago is to say, take your region and break it up into lots of little pieces. Okay, sure. That's nice, but is it practical? Well, we want to use our tools. We say, okay, well, let's not think of breaking our region up into little pieces. Let's think of taking it and breaking it up into strips. So I'm going to do little strips. So let's fix one of our variables, and suppose for a second we fix y. So if we fix y, what that means is we're taking a slice in this direction. And so we come up to our curve, and we have that. So I'm going to pull this slice out. And now what happens is we have a picture in, if you like, the xz plane. And it looks like we're doing something like that. So here's that slice. Okay, so what's our idea? Well, if we're going to think of things in terms of volume, we can say, well, our volume, we can think of it as our sum of, let's see, what do I want to say? It's area of the slice times the width of the slice, which is a small bit of I, delta yi. So how do you find the area of a slice? So let's think about it. Well, this is the function f of x comma y. But in this case, y is fixed. How could you find this area? What would you do? You'd integrate. So you say, okay, so then this is the sum, the area of slice would be the integral a to b f of xy dx, because we're in the x direction. That's your area of the slice, delta yi. Now notice, this is a function of two variables, x and y, but we're only integrating with respect to x. How do we treat y as we integrate with respect to x? As a constant. Now you might say, but okay, how do I think of that constant? Well, essentially what it's doing is every y is a slightly different function, and so you'll get a slightly different integral, but you still, as you're doing this integral, you think of it as a constant. You say, all right, good. Well, now what? Well, now you just keep adding. You do smaller slices. So we're going to integrate, add up all the individual slices. So that's integrating c to d of integral a to b f of xy dx dy. So, what's the procedure? You first work on the inside, carry this integral out with respect to x. That will become an integral with respect to y once you're done. And then you carry out the next layer. So the good news is, when we do integration in this way, it's the same integration that we learned before. We just get to do it twice. Now, I will say that we could have sliced in a different way. What's another way we could have sliced? We could have x fixed. So if x is fixed, that means we're going in that direction. And then we can, again, look at the slice here. So what you get, you have a slice now from C to D. And it'll look slightly different. Okay, it might look like this. But you still have this function f of xy. And it's the same basic idea. So we say, well, the volume is approximately the sum, the area of the slice, times the width of the slice, that's delta xi. But we say, look, we know how to find this area. It's the integral c up to d of f of xy dy. And so this becomes the integral a to b, integral c to d, f of xy dy dx. Okay, so notes. This is what we call iterated integrals. You integrate one variable at a time, and you treat the other variables as constant. You often get a choice. You say, well, which order do I want to integrate? And you have to be careful. Notation is important. And before we get to notation, it's important, I just want to emphasize, work from the inside out. You have to do the innermost layer before you can do the next layer. And it might not seem like a big deal now, but it's going to become a big deal next week. Okay, so why do I say notation is important? So in Calc 1, we tried to drive home. Write down your dx's with your integrals, or write down your dt's, whatever your variable was. And you were probably like, why? Does it even matter? Why do we do it? Well, it does matter, because it's telling us information here. So what it tells us is when I see a dx dy, that tells me that the dx ties to the inner integral. So the bounds there, a to b, are x bounds. X equals a to x equals b. The dy, in this case, ties to the outer integral. Those are y bounds. So we go from y equals c to y equals d. And in particular, there's this important idea. The bounds here are storing your region. And one of the biggest things that we'll have to get to is get to the point where we're comfortable with saying, how can we describe our region? If you can get to that point where you say, I can describe the regions I'm integrating, you're going to do great. So let's get there. We're going to be doing lots of practice, and we'll be picking it up next week. But right now, rectangles are very easy to describe. There's not a lot of things that can happen with rectangles. All right, so that's the philosophy. Any questions? Yes?
Does it matter what order you take the integrals?
Oh. I have the answer to that on this. Okay, so I'll say it out loud now, and then you'll see it written in a second. Yes and no. So let me explain the no. It doesn't matter which order you take the integral in that you will get the same answer at the end. Yes, in the sense that sometimes the way to get there can be either easy or impossible. And sometimes it doesn't matter at all. And so order of integration can make a big difference. And I will tell you, they love writing problems that say, change the order that you integrate. And essentially what that's doing is, by changing the order you integrate, you can turn an impossible problem into a possible problem. But the other reason they like to do that is when we ask people to change the order of integration, we're really testing, do you understand how to describe regions? So they do like asking that question. So yes and no is the answer. Yes?
Are we only going to do this with definite integrals?
Okay, so are we only going to do definite integrals? Definitely yes. We are not going to talk about antiderivatives. Or are we? Not really. We're only going to be dealing with definite integrals. But there is sort of, we want to build up, the real fun punchline is to say, remember that fundamental theorem of calculus we talked about in Calc 1? Because it was fundamental. And we enjoyed it because it had the word fun. So we had to enjoy it. We're going to take that and say, let's do it like 4 times in different settings. Like, oh, here's a different one-dimensional setting. Oh, here's a 2-dimensional setting in the plane. Why stay in the plane? Let's go 2-dimensional in 3 space. Why stay in 2-dimensional? Let's talk 3-dimensional. So we are going to go through all of that. That's like the big denouement of the semester. So in that sense, there'll be a little bit of this notion of sort of antiderivatives. But for the most part, antiderivatives don't quite make sense. And so we are going to be focused on definite integrals. Other questions? Now that I've spoiled all the surprises for the remainder of the semester, that's all right. That's okay. I'm sure we'll surprise you once or twice. All right. So that was the comment in the upper corner. It doesn't change the answer, but it might simplify the process. So let's do this one together, and then I'll give you one to do by yourselves. So our together one. Find the volume between z equals xy squared and the xy plane for x from 1 to 3. Oh, and it should have said 0 less than or equal to y less than or equal to 3. That's a typo. What's another name for the xy plane, by the way? Z equals 0. So if you see xy plane, it's just code for saying z equals 0. And you'll notice that since x and y are both greater than or equal to 0, this function xy squared is greater than or equal to 0. And so how do we find a volume? Well, think of, how do you find an area between 2 curves? What did you do? Yeah, you took like top minus bottom, and you integrated. Now we have 2 surfaces, xy squared and 0. How do you find volume? Top minus bottom, and you integrate. So our volume is the integral over our region of xy squared dA. So now we've come to the point where we get to do a choose your own adventure. So our 2 options. Well, we can integrate xy squared dx dy, or we can integrate xy squared dy dx. Okay. Now these integrals aren't done yet. We have to set up our bounds. For the first integral here, the dx dy, I set the bounds, well, there's a couple ways here. Let's go from the outside in. Where does y go from? 0 to 3. So this tells me the outside layer is my y layer. So these are my y bounds. So I'm going from y equals 0 to y equals 3. Where am I going for my inside? 1 to 3. Because I'm going, these are my x bounds. So x goes from 1 to 3. Okay. Here, on this integral, what are my outer bounds? 1 to 3. What are my inner bounds? 0 to 3. And you might say at this point, it's like, haha, switching order of integration is easy. You just whoop, flip the bounds and life is good. Wait till Monday. We will tell a different story. Okay, the answer will not depend on which one we do. Which one do you want to do?
Going down.
Going down. All right, this one. Okay, so let's work this out. We're not doing the outer integral. What's the integral of xy squared with respect to x? Well, we're integrating, not differentiating. So we're integrating. The y squared here is acting in what way? Constant. So it's like we're integrating x. So it'll be 1/2 x squared y squared. And now we evaluate. And to help us remember what we're evaluating, I like to emphasize it by putting down, we're doing the x bounds. We're plugging x's in. So from x equals 1 to x equals 3. All right. Well, what will this become? Let's, before we integrate, plug it in. So when we plug in 3, we get x is 3, so that's 9/2 y squared. X is 1. Subtract 1/2 y squared dy. 9/2 subtract 1/2, also known as 4, 8/2. All right, what's the integral of 4y squared with respect to y? 4/3 y cubed. And evaluate y equals 0 to y equals 3. Again, I like to emphasize what I'm evaluating. Now, at the last stage, it doesn't really matter, but at intermediate stages, it does. Okay, when you plug in 0, good news, you get 0. What happens when we plug in 3? We'll get 27. 3 cubed is 27. We're dividing by 3. So that gives us 9. And don't forget the 4. So 36. And you can check. You will get the same if you do the other integral. All right. So, any questions? Okay. They were both easy. Now try this one. Find the integral over the region x e to the xy dA, where R is the region where x goes from 0 to 1 and y goes from 0 to 1. If you integrated with respect to x first and then with respect to y and you were able to get the answer, I'm impressed. You should start teaching the class. Because it's crazy. What was the number? E minus 2. All right. So, now the thing is that why does the dx dy not look good? Well, if you're integrating with respect to x, you have 2 x's. And so what technique would you have to do? Well, integration by parts. And that feels like having to remember stuff. And I'm not a big fan of that. But if you integrate with respect to y first, there's only one y. And that doesn't feel like I have to remember anything. So I like that. So if you try integrating with respect to y, the question is, what happened to the x? Well, what happens is there was an x. When you integrate e to the xy, you have this constant upstairs. When you integrate e to a constant y, you have to divide by the constant, so the x is canceled. So the things which was making it terrible all of a sudden went away. You evaluate y equals 0 to y equals 1, and you said, I'm left with an integral I'm okay with, and you got e minus 2. All right. So to finish up with today, I will say that there is a nice, useful fact that I pull out from time to time, and I just want to mention it here. And it deals with integrating over rectangles. So this does not apply in all cases. You have to be in some very specific situations. Namely, your bounds have to be rectangle-like. So there can be no variables in your bounds at all. Your bounds are strictly numbers. So that's a rectangle. And it says functio. It probably should have said function. I should fix that. Nobody noticed that. Function, you need to be able to write as function of x times function of y. So you can't have them like mixed together. But if you're in that situation, then what you can do is you can say, this first integral is with respect to y. How is g of x with respect to y? The answer, it's a constant. You pull it out. And you say, okay, now I have this integral. But notice it's a definite integral, which means it's a constant, which means you can pull it out. So what it says is this two-dimensional integral is really the product of two one-dimensional integrals. So it basically says you can integrate in parallel. All right, that's it for today.